ACL is over. Time to get back to physics. I know he didn't show up. I wish he had been there. I would have gone if he had been there, but he wasn't. If you have never been to ACL, your homework for next year is to go to ACL. Whether you're a junior or senior, get there. Today, however, we're not talking about ACL the whole time. We're mostly talking about work and energy. So it turns out that a lot of the problems we did last unit with forces, we can do with energies instead. Not all of them, but some of them. Some problems we have to use energy. But if we have a choice, we like energy better. And why we like energy is because energy is a scalar. Remember, a scalar means I have no directions on those. And so that means that I don't have to use sine and cosine as much. So if I have a scalar, I have less. I still have some sine and cosine. And while we like sine and cosine because they let us do problems, the least amount of that we can do, the better, because we might make some mistakes with it, and we wanted to get it right. So because energy is a scalar, it tends to be a little bit easier. So when we get a choice, we like to pick energy instead of forces. Also, another nice thing about energy is we can have the same equations each time. When we did forces, you remember we did free body diagrams, and every time we did it, our formulas were a little bit different, and so it got a little complicated. We have nice, simple equations for energy. We always use the same ones, and so it tends to be a little simpler in energies. And the last thing is, with vectors, some of what threw us off was when things were positive, when things were negative, and friction flipped sides sometimes if it changed directions, and that was kind of confusing. If we do energy right, and I'll show you how, we can make sure that all of our energies are positive. So everything is positive, no negatives to throw us off. That has something to do with the scalar business too. But all of that together means we like energy more than we like forces. And if we can do things in energy, we do. Before we get too far into energy, let's talk about where it comes from. Energy comes from work, and work is the amount of energy we transfer to an object, and it comes from essentially force. When I push on an object, say I have an object right here, and I push on with a force of 5 newtons, and it moves a distance 2 meters, I'm giving it some energy. And my equation for that is that the work equals force times distance, or in this case 5 times 2, or 10 joules. And joules is our units for energy and work. And our equation for work also says that this equals the change in energy in a system. So it turns out that it's not the whole force that I care about. It's only the force that's in the same direction that I'm displacing the object that matters. So if I'm moving it this way, I have my force of 10 newtons that's at an angle. It's not the whole 10 newtons I care about. It's only this part, the part that's in the same direction as my displacement, because this part here is going to be canceled out by normal force, and that's not going to add the energy to the energy of my object. So really, I could rewrite this to say that the work equals the force parallel times distance. That probably is a better explanation of that, to put the little parallel in there. You can sometimes do it the other way and say it's the displacement that's in the direction of the force, but this is the way we usually do it. So in this one, we'd have to take this component, which is going to be 10 cosine theta. Yeah, and I know I said we weren't going to use cosines. We do it a little bit. So this is going to be 10 cosine 30 times 5 to find out how much energy is added to this particular system. Our next concept is power. Power is the rate at which work is done, and rates we've talked about a lot. You know, velocity is the rate of change of displacement, acceleration is the rate of change of velocity, so we know what rates are. It's when we divide it by a time down on the bottom, and power is the same. Now, the kind of questions we get of this is they'll say how much energy is given off if we have a power of 50 watts going for 30 seconds. And, you know, you take the 50, put it in there, 30 there, multiply them together, and get the work. And we know work is the change in energy. So somewhere in our head, start like equating work with energy. Work is measured in joules, energy is measured in joules. They're basically the same thing. This is the main equation we use. Now notice, because we have it divided by time, a lot of those graphing things we did with displacement are gonna work for power as well. We'll talk about that a little later. We have another equation for power, just like we did. We talked about other rates. There's an instantaneous power. At 1 second, the power is force times the velocity. And occasionally we'll set one of those, find it, the instantaneous, and say if it was that, and we did it for a certain amount of time, what is the energy? So you can set the two equations equal to each other. In general, this power stuff is done a lot with graphing, and it's done a lot with kind of simpler equations. All this stuff is sort of getting us ready. This unit snacks are all going to be beverages, and we're going to start with the king of beverages, classic Coke. The only beverage ever that people had a riot when we tried to change it. But they did change it, and you didn't necessarily notice it. But here, this is my favorite thing about Coke. I love listening to this. Are you listening? Here we go. Nice. Oh, I'm spilling over. Oh. Nice. Oh, Skrillex is excited too. My Coke spilled on the thing. Started to sing. But I like, look, I like watching the bubbles go in there. Wow, that's nice. If you do get Coke, I know some people think Coke is the evil empire. Don't believe them. Get this kind of Coke. This Coke is actually bottled in Mexico, so they use real sugar. Tastes better for you. Stay away from that high fructose corn syrup. That's how they changed Coke secretly. Nobody had a riot, but they should have. Have this kind, not the other kind. Have some. It's pretty good. Okay, this slide is the main part of energy that we do for this chapter. And we have three kinds of energy: gravitational potential, kinetic, and spring potential. We need to be able to calculate them. The first one, we've probably heard of this one before, this MGH business. And G, we definitely know what that is. This one is the amount of energy that's associated with how high you are up off the surface of the Earth. So the farther away you get, the more potential energy you have. And you know that's true because if you let something go, it starts to move. It had some potential. And for this, the mass is important. My G constant 9.8, and the change in height is important. Because this is a change, we have to set a 0 point when we're doing problems with gravitational potential. And usually the best place to put that is the lowest point an object gets in the problem. So if we have a ball that's up 5 meters in the air, and it falls down to the ground after we drop it, we're going to set this bottom part to be my 0 point. Because that's so important, you need to actually write it on every problem so we know where that 0 point is. Once you set the 0 point, you have to do the whole problem with that as a 0 point. But in this case, like it would go, all the MGH would go into 1 FMV squared when it gets down to there. Sometimes we'll set the ground to be the 0 point, even if it never makes it to the ground, because they give us all the heights in reference to that, and it makes more sense for us to do that. But a lot of times it makes a problem really easy if we make 1 point to be the 0 point that the actually gets to, because then the MGH goes to nothing, and our calculations are easier. Kinetic energy is really easy. Whenever something's moving, we have kinetic energy, and it's just 1/2 mv squared. Notice it's got that squared in there, so that changes some things. We always get a positive value for this, because when we square the velocity, which is the only thing that could be negative, we get a positive value. If we set our 0 point to be the lowest point in the problem, we never get a negative h. That's the good thing. And for spring, remember, if we have a spring, we're going to move this that way as our x. How much it's moved from its unstretched length is x, times that squared. And again, so that means if I go forward or positive or negative, I'm still going to get a positive value there, times a constant, 1/2 of that, always get a positive there. And so I'm always going to get positives for all three of these. Makes my life a lot easier. Remember, we said that we could not use kinematics on springs. And so we use the ESP more than we use any of the other types for springs. If it's a spring, generally we need to do energies, and we use this one right there. Okay, so these are the steps to solving an energy problem. When I get an energy problem, I want to draw a picture, but a specific type of picture. I want to draw a time-lapse picture. And the reason why is because what allows me to solve energy problems is that energy is always conserved. If I know the energy here and here, I can set them equal to each other and solve for things that I don't know. So drawing a time-lapse picture allows me to draw an object at a lot of different places and then find the energy of those different places and set them equal to each other. So when I'm drawing a picture, I'm going to draw an object at 2 different places. Like I have an object on a cliff and I'm throwing it off. Time-lapse picture. My ball is here. My ball is here, my ball is there, it goes to the air. I know all those different places. My next step is to set a 0 point because I know I'm going to use gravitational potential for almost every problem, and so I want to have a place that I'm measuring all my heights from so that I'm finding the changes. If this is my problem, I'm going to put my 0 point down at the bottom. Again, I want my h's to be positive, and I also want one place where it's going to be 0, so that helps me. Sometimes I choose the ground. In this case, there's kind of 2 at the cloth from the bottom, but the bottom part is what I want. Then I'm going to find ET at the beginning. They almost always give me most of my information at the beginning. I'm going to actually put on my picture, like this is where I'm finding ET, so that I have a reference point. Then I put all the things into my equations. I have gravitational potential, kinetic, and spring. For the first couple problems, I'm going to write all 3 of them out and then put zeros in there to get rid of things, because one of the benefits of energy is that I always use all those problems. Now later on I might take some shortcuts when I know there's no velocity or no x. I wouldn't put them in there, but for the first couple ones, go ahead and write them all in. If you don't know something, like you don't know the initial velocity, you can leave v as a variable. Most times at the beginning they tell you everything, and later on you don't know something. And then I'm going to find ET somewhere else. Let's say in this problem I'm going to find it at the very end. I put ET on there again, but I want to say it's at some other time, so I put a prime on it. Find the exact same equations. I'm always going to have gravity, kinetic, and spring potentials. I set them equal. This time maybe I don't know how fast it's going, so I'll leave v as a variable. I'm only going to have one variable usually. If I end up with more than one variable when I have the 2 different energies, I've probably done something wrong. I should look back at my problem. But I'm going to set those 2 energies equal to each other and then solve for what I don't know. And occasionally you may have to do a collision or a kinetic problem before. Sometimes like you'll find the v at the end and maybe you have to collide it with something else. We haven't even really talked about collisions, but you'll know what those are in a bit. Sometimes you have to do more than one energy. Like they'll say, okay, now that we know how fast it was going there, how fast was it going up here? And so sometimes you put ET double prime, let's find energy there. But it's not any harder. You do the exact same equations everywhere. Energy problems are pretty straightforward. Just follow these steps and you'll be good. So let's do an example. So here's my example problem. And I went and drew the picture to save a little bit of time. They would write this problem by saying that I have a ball being thrown exactly horizontally at 2 meters per second off a cliff. The ball is 1 kilogram. The cliff is 50 meters tall. How fast is the object going at the base of the cliff? Drew the picture, then I set my 0 point down here, and I say, okay, let's go ahead and find ET with our energy total equation. That's the general form of our equation. And we look at this equation though, and we want to try to think about it a little bit before we start. We know there's a key variable in all of these. Mass is always a constant, g is always a constant, h is what can change, and v is the one to change in this one, and x is the one in this one. And so we look for those variables to know when they're 0. Now we have a height at the beginning, so that one's going to be there. We have a velocity, but this one here, there's no compression of a spring, and so I can cross that one out and not even put any numbers into it when I'm finding this. So when I find my ET, which is what this is, I'm going to get the mass, which is 1, times g. I'm going to use 10 times the height, which is 50, plus 1/2 times 1 times 2 squared. When I do that, I get a nice easy 500 here, and 1/2 of a 2, so I get 2. So I end up with 500 joules as my answer for that one. And so that's going to be my energy there. And because it's my energy there, it's going to be my energy for the whole rest of the problem. So I can set any other energies equal to 500 to get some answers, and that's what I'm going to do next. This time when we do ET prime, we're going to do it down here at the bottom. Now ET prime is going to have no height, so this one's going to go to 0. Again, no spring, and so all we have for ET prime is 1/2 mv squared. So I get 1/2 times 1 times v squared. So essentially I get 1/2 v. And so I'm going to set this, which is 1/2 v squared, equal to 502 joules. Oh, that should be 502. And I'm going to solve for my velocity. I just take 502 times 2, 502 times 2, and then I square root it. And I get v equals 31.69 meters per second. And so that ends up being pretty fast. Like I just do ET prime, set them equal, and solve. And so energies end up being a little bit easier. Yeah, no vectors, no sines, no cosines, pretty straightforward. Okay, gotta talk a little graphing stuff. I know the first unit we hit graphing pretty hard. Second unit, those same things applied a little bit because you could find force and acceleration, but we didn't do too much graphing in the second unit. We're coming back to a little more graphing this time, a little less stressful than the first time. But you remember that when we had an xt graph and we knew that the velocity is x divided by time, we could find the slope of that graph to find the velocity. And now we find ourselves with an equation that's very similar. We know powers work over time, just like velocity was displacement over time. And so whenever we have a nice easy one thing divided by another one, we want to find that thing, the slope is going to equal it. So on a work time graph, we can find the slope of the line and it gives us the power, just like on an xt graph, the slope gave us velocity. Makes sense, it's very similar, but that means that anytime we have an equation that's one thing over another, just doesn't have to be time, it can be anything, we can find the value by finding the slope. Similarly, when we went backwards from a velocity time graph to x, we knew that x was velocity times time, and so if we end up with an equation that's one thing times another, in this case work is force times distance, just like x was velocity times time, when we have a force distance graph, the same way we had a velocity time graph, we can find the area underneath this curve to find the work. We'll have a couple examples of that. It kind of makes sense, and I think that you'll get it, especially once we have a couple examples. It'll be fun. So all the forces that go into ETs and ET primes and ET double primes and all those things are all called conservative. And they're called that because when we put energy into them by throwing an object upwards, for instance, it's easy to get the energy back out and get it into velocity. There are some forces called non-conservative forces, and they are forces where once the energy gets put in there, it's really hard to get back out. Friction is our main example. So conservative forces are our ET forces. But if we get energy that gets lost to non-conservative forces, we can't set it equal later on because it doesn't go away, it just goes into a form we can't get back to get into velocity. And what we do for those is we do work. And so our normal equation says that ET equals ET prime. But sometimes we have to say ET equals ET prime plus the work done like to friction. And if we do that, we just have to find out what the frictional force is and how far it's applied. Because remember, the work, in this case friction, would be the force of friction times the distance over which it's applied. And work is essentially another kind of energy, and so that kind of makes sense. It's just that it's not something we can get back from it. And so once it goes in there, it's kind of lost to the other kinds. It's not lost, like it's still there, just we can't use it. Okay? So I know I told you we have less sines and cosines for energies. We do occasionally have some sines and cosines, mostly having to do with some distances, because they'll give it to us in the wrong place. And so I wanted to mention two of them really fast because they're so common. One is they like to do ramp problems in energy just like they did in forces. And when they give us the distance along the incline, we know that our equation has height. And so a lot of times they'll give us that distance and the angle, and we'll have to solve for the height over here to plug the height into MGH. That kind of makes sense, but just to warn you that it's ahead. A little more complicated example of that with another height is when we have a pendulum. That's what this is, and this is a person swinging down. And when you have a pendulum, a lot of times they'll give you the length of the string up here. They'll give you the angle. And we know that the string length doesn't change, and so I have that same length down here at the bottom. I don't want to know that length. I want to know how high it's changed. So this little h here. And so I have to go ahead and find this little green thing right there. I like to call that green thing squiggle bit. I put squiggles on it. And that squiggle bit thing is going to be the hypotenuse, which is L, times the cosine of the angle because it's the adjacent side. And so we get this little squiggle bit thing right there. And it's L cosine theta right here. And then that's not what we want. We want h. And so the whole thing is h. We subtract squiggle bit, which is L cosine theta, and h is L minus L cosine theta. And we do that so often that you kind of have to memorize that. If you needed to, you could draw the picture and do it, but it will save you time in the end to know that the height of a pendulum going down is L minus L cosine theta. That's it for work, power, and energy. I think you should go watch this video. I love this video. It's amazing. Everyone should see it. I'm sure you have already, but do it again right now. It's time. In the meantime, write some comments down there about energy and what you do and you don't get. And I will see you next time in class.